We have sent rovers to comb the sands of Mars, probes to the edge of the solar system, and telescopes that peer back toward the Big Bang. Yet, for 5 decades, human beings have remained confined within low Earth orbit. The furthest reach of human exploration remains fixed at the historical benchmark set by the Apollo missions. Current mission architecture aims to establish a permanent, sustained human presence in deep space. To meet that goal, Artemis II will carry 4 astronauts on a journey 400,000 kilometers away from Earth, the furthest distance any person has ever traveled. Constructing a long-term outpost requires physical proof that this hardware can sustain human life in a deep space environment. Artemis II is the mission designed to provide that data. Breaking Earth's gravity requires the Space Launch System, or SLS. At liftoff, its side boosters generate 3.6 million pounds of thrust, making it the most powerful human-rated rocket ever built. This design utilizes refined engineering from the Space Shuttle program, specifically reusing the liquid-fueled RS-25 engines that once powered the orbiter fleet. During the uncrewed test in 2022, this level of combustion turned the pitch-black Florida night into daylight for miles around the launch pad. Attached to the very top of the crew capsule is a specialized spike called the Launch Abort System. If the flight computer detects a loss of engine performance or a trajectory failure, 4 motors will instantly pull the capsule away from the rocket, allowing the crew to parachute safely clear of a potential explosion. To account for this, Artemis II is scheduled as a night launch in Florida. If a high-altitude abort triggers, the capsule would land halfway around the world near Africa. The timing ensures the crew splashes down in bright daylight, where rescue teams can maintain a clear line of sight. In space, the spacecraft enters a highly elliptical Earth orbit, swinging from a low point of 185 kilometers to a peak of 70,000 kilometers. This holding pattern provides a several-day window to monitor life support machinery and the new waste management system. Validating the maneuvering thrusters is a safety priority, following recent issues with other capsule designs that left astronauts waiting months for a return flight. Pilot Victor Glover will take manual control to execute a simulated docking maneuver. He will steer the Orion capsule back toward the ejected second stage of the SLS rocket, using visual targets to test the precision of the thruster array. This manual control must be perfect, as future missions rely on the capsule physically docking with a separate lunar lander to reach the surface. Once the checks are complete, the engines ignite for a translunar injection burn. This places the spacecraft on a free return trajectory, where gravity slings the capsule around the Moon and pulls it back toward Earth in a continuous loop. During the transit, the crew will conduct biological tests and practice deploying an emergency radiation shelter beneath the floorboards. This storage area, surrounded by supplies, provides extra shielding against sudden solar flares. On day 6, the capsule reaches the Moon, passing over the lunar far side at altitude of 10,000 kilometers. While Apollo missions passed within 100 kilometers of the surface, this 10,000-kilometer altitude allows the crew to capture the widest, most comprehensive visual data of the lunar landscape ever recorded. The final phase of the mission is the most dangerous point in the journey, re-entering the Earth's atmosphere. Returning from deep space requires the capsule to hit the atmosphere at 40,000 kilometers per hour. Friction will drive the external surface temperature to over 2,760 degrees Celsius. If the heat shield withstands these forces, the capsule will splash down in the Pacific Ocean near San Diego for recovery. Artemis II functions as the grueling stress test required to transition human exploration from brief visits to a permanent presence in the deep space environment.